Hello students, this is Mr. Allen. Today we're going to look at a very important application of differentiation, which is optimization problems. The objective today is simply to solve applied minimum and maximum problems. We already have seen how to find mins and maxes. Now we're actually going to apply those to real world problems. So a manufacturer wants to design an open box having a base that's square and a surface area of 108 square inches, as shown in this figure. What are the dimensions of the box to maximize the volume? So this is something that you can imagine as a manufacturer. You're making this box. Now, please note it doesn't have a top, but we want to maximize the volume based on that 108 square inches surface area. Now, since the base is a square, we know that the surface area, the bottom of the box is just going to be, if we go x by x, is going to be x squared. And then there's going to be four sides, with each side having a base length of x and a height of h. And there's four of those, so that's 4xh. So that gives us an equation of s equals x squared plus 4xh equals 108. This is actually going to be our secondary. We'll talk more about that in a minute. This is going to be our secondary equation. And the reason it's our secondary equation is the primary equation is always whatever it is you're trying to do or maximize or minimize. In this case, it's volume. Now, volume of a rectangular prism in this case is length times base times height. But in this case, since we know that the base is x squared, it's just x squared h. This is our primary equation. This is what we're trying to minimize, or in this case, maximize. Yeah, there we go. So I just said that. So the surface area of the box is the area of the base and the four sides, which we've already discussed. That's our secondary equation. Because v is to be maximized, we want to write v as a function of just one variable. So if you'll notice here, we have two variables, but now what we can do is we can use our secondary equation to write that into one variable. So to do this, we can solve the equation x squared plus 4xh1 equals 108. That's our surface area, our secondary equation. We can solve this for h. And the way we would do that is we would minus the x squared to the other side, and then we would divide by 4x. So this is our secondary equation. I'm sorry, this is our secondary equation solved for the x variable. Now what we can do is we can substitute that into our primary equation. Our primary equation here is x squared times h. And we made that substitution here in pink. And we can clean that up a little bit by using the distributive property. Now we have our volume function written in terms of just one variable, and that variable is x. Now what we're going to do is go ahead and proceed and use the techniques we learned in section 3.3 and 3.4. Before we go ahead and do that, though, let's talk about a feasible domain, and that means realistic numbers that we can put in here. Which values of x would make sense for this problem? Would it make sense to have x equaling -1, let's say? Would that make sense? Can we have a length of negative? That doesn't make sense. Would it make sense for x to be 500? Well, it turns out the answer to that is no as well. So I'll let you play with this, but hopefully you can figure this out on your own. We need to make sure that we are within the actual restraints of this particular surface area, which is 108. So hopefully with a little bit of work, you can determine that x has to be at least 0. And technically, I'd even argue it can't be 0. And it has to be less than the square root of 108. Otherwise, that surface area of 108 is not possible. All right, so let's go and do the derivative on both sides of this equation. So dv dx turns out to be 27 minus 3x squared over 4. We want to set that equal to 0. We don't need to worry about setting it to d any in this problem. So now we're going to just simplify, and we get two critical numbers. We get x equals plus or minus 6. Now please keep in mind that we just talked about that the feasible region is 0 to the square root of 108. Right? This is our feasible region. So this x, we can just discard that. That can't be part of our solution. You can't give a length of -6. And so we can go ahead and evaluate this to figure out what our volume is going to be. So if V is 0, that's one of our endpoints. That turns out to have a volume of 0. If V is 6, we get 108. And if we do V of the square root of 108, by the way, this is a critical number. This is a critical number. Oh, I'm sorry. This is not a critical number. That's an endpoint. And this is the other endpoint. So obviously a volume of 0 and a volume of 0 is not going to be maximal. So it turns out that our maximum volume is going to be 108. Which tells us, I'm going to erase everything on this slide here real quick, which tells us that when x equals 6, sorry, when x, make sure we got the pin in. When x equals 6, this is going to give us the dimensions with the maximum volume. So x is 6, it turns out that h will be 3, and that will maximize the volume. Okay, so here are the guidelines for doing these applied max and mins or these optimization problems. First thing I would recommend that you do is make a sketch of whatever it is you're trying to do, if possible. In this case, we were dealing with a rectangular prism. Try to figure out all the given quantities and any quantities that need to be determined. Typically, you want to come up with some sort of primary equation that you're going to substitute or manipulate to make our secondary equation. We're going to try to substitute and manipulate that back into our primary equation. Remember, the primary equation, and this is key, the primary equation is what we're trying to maximize or minimize. And then the last thing we want to do is we want to make sure that our answers make sense. It wouldn't have made sense on that last problem to have an x equals -6. Let's look at one more example here. Let's try to find the minimum distance. The first one we maximize, so let's do a minimize. It says which point on the graph of y equals 4 minus x squared is closest to the point 0, 2. All right, so here's our curve, this parabola, which hopefully you're aware that that's a parabola. And we've got this point 0, 2, which would be right here on the graph. And we want to try to find where the point on the curve will be minimized. So the distance from the point 0, 2 to the point of the curve is minimized. Now you'll notice that there's going to be two answers here. Just if we look at it graphically, if you don't sketch the graph, sometimes it's really hard to see this. That's why I recommend you sketch the graph. Now, don't forget that there's a distance formula that's going to be applied here. And by the way, the distance formula is basically what we're trying to minimize. We're trying to minimize distance. So this is going to be our primary equation. Hopefully you're familiar with our distance formula. Remember, our distance formula is the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So in this case, we put 0, 2 because that's the point we're using. We still got to figure something out though. You'll notice that our equation D has two variables, x and y. So what we can do is we can use this in as our secondary equation. Our secondary equation in essence is this parabola. In other words, y, we can substitute 4 minus x squared. So that's exactly what we're going to do. We're going to change this y to 4 minus x squared. We're going to clean that up and we get this nice little expression here. Now we're going to go ahead and do some calculus. But before we do that, I would argue this. You can disregard the square root. You do not have to, but you can get rid of the square root. I claim that if you minimize this function, you are also minimizing this function. So the square root really doesn't have any impact on the minimum or the critical numbers. Plus, it makes it a lot easier to deal with. Note the domain of this function is the entire real number line. So there's no endpoints and the domain is all real numbers. So let's go ahead and do the derivative, which is very easy using our power rule. We'll get 4x cubed minus 6x. That can be factored. So hopefully from there you can see that we have three critical numbers. Clearly this is when x is 0, so that's the 0 part. And then when you solve this equation, the 2x squared minus 3 equals 0, that's going to yield these two values here. All right, so now we can just use the first derivative test and we can determine that x equals 0 yields a relative maximum, which is not what we're wanting to do. Whereas x equals the square root of 3 over 2 and negative square root of 3 over 2, those yield our minimum distances. So the closest points are square root of 3 over 2, comma 5 over 2, and negative square root of 3 over 2, 5 over 2. So I've done two examples here. I've done an example where we maximize the volume, and now we've just done an example where we minimize distances. Please keep in mind in both examples, we drew pictures. And I mean, obviously I had them drawn beforehand. We drew pictures. We had primary and secondary equations. And in both problems, we took the secondary equation to help us reduce that primary equation to one variable before we do our calculus stuff. That's a good place to stop. Thank you for your attention.